So the topic is ISS depth imaging without a velocity model. And there's a paper, what are all those? There's a paper that we have copies of, which was the documented first field data of ISS depth imaging, which had an argument to explain why that was successful, yes? In other words, how do you know that that method was successful? So we go through a detailed discussion with a set of synthetics and then the field data to provide a compelling argument for that initial test. So Zhenzong is distributing that paper. That was a few years ago. So we want to try to explain, to give you some sense of how is it possible to do depth imaging without a velocity, yes? And how does the mechanism work? So it sits over here. After all these pre-processing and multiple removal occur. So consider this one-dimensional normal incidence equation just to get started. So here's this single frequency 1D normal incidence acoustic wave equation with that familiar 1 minus alpha function, where alpha characterizes the difference between the actual velocity as a function of depth and the reference velocity. And you have this operator, and we, as usual, we're going to expand alpha as alpha 1 plus alpha 2, where alpha 1 is the portion of the difference between actual velocity and reference velocity that's linear in the data, alpha 2 quadratic in the data, and so on. And then you have these equations that we derived yesterday that show that's for the second and higher term. The first term is just G0 k squared alpha 1 P0 is the data, and that gives you a formula you could invert for alpha 1 from this formula. You get this analytic form. So if you look at a detail of what these equations become for this simple case, these V1, V2 are very general. V is any difference between L0 and L. Any operators could be elastic, could be electromagnetic. This methodology is applicable to many fields. Okay, so, but for this simple case, where V1 is just k squared alpha 1 and so on, these equations here, the second equation in particular that we're going to be looking at, becomes minus a half alpha 1 squared plus the derivative of alpha 1 times this integral. So remember, alpha 1 is linear in the data. It's essentially an integral of the trace, okay? So you have alpha 2 is quadratic in the data, as promised. It's a contribution to alpha that's quadratic in the data. Alpha 3 is similarly cubic in the data, yes? So let's just look at the function of these two terms here. If you have just a single reflector, in other words, if your model consisted of just the following, C0 and then C1, just, okay? Two half spaces, you send in some wave, comes back some scattered wave, you take this single reflection coefficient, let's call it R1, that comes from this reflection data, and you substitute that spike, you send in some spike wave, and back comes a spike with an amplitude R1. If you put that in the formula to solve for alpha 1, you get alpha 1 is 4 R1H of Z minus A, where A is this distance. In other words, I give it C0, and so it locates that alpha 1 is a jump, a heavy side at A, and it has an amplitude 4R1, this linear. It turns out alpha is a relationship, in this simple case, 1 over C1 squared is 1 over C0 squared times 1 minus alpha. In other words, they're just numbers. They're not, it's not a function. In other words, in general, this is C of Z and alpha of Z. But here it's just a number, yes? And so alpha, therefore, is a relationship, something that cares about C1 and C0, yes? Some kind of difference there, yes? In this case, alpha is a number that there's another number that cares about C0 and C1, and that's R1, the reflection coefficient. R1 is C1 minus C0 over C0 plus C1 or something, yes? So R1 and alpha both are functions of C0 and C1. You can express one in terms of the other, turns out. And so there's a series. You get alpha equals, for this simple one interface, is 4R minus 8R squared plus 12R cubed, and so on. 1, 1. Yes, this is the alpha, okay? That number, alpha, this number, where this is C1 and C0, this number is expressible in terms of R1 with a series. This is the linear, this is the portion of alpha, the amplitude. In other words, there's only an amplitude issue here because it's well located. This thing is already well located. In other words, alpha 1 provides a jump at A, and that is where alpha jumps. Yes? You understand? There's not a mislocation issue. So this, if you take this form, alpha 1, and place it in this second term here, the second term of alpha 2, you'll get identically 0. Okay? You'll get a 0. You'll get a delta evaluated by something, and h of a negative. Okay? A heavy side of a negative is 0. You understand? In fact, you have to make it 0 to z minus epsilon. You have to make it so that they're not quite that upper limit. It relates to the epsilon of the internal multiple, by the way. There's always an epsilon. In other words, so the point is that, why did I just say this? If you have this type of unknown, the only unknown is the amplitude of the jump. You gave me the velocity, C0, so I know the location, yes? The location's right. The linear is giving you a linear approximation to the amplitude of alpha, yes? If you look at this term, alpha 1 squared is going to be 16R1 squared, yes? Alpha 1 squared, 16R1 squared. Minus a half gives you minus 8R squared. It's giving you the second term, you see? So this guy over here, this term, is dealing with amplitude issue. This guy is dealing with mislocation, it turns out. If you give me two interfaces, in other words, A and B, like it's in this slide, in other words, make it that the first reflector is at A, the second reflector is at B. Actual depth. This velocity is C1, C2, whatever. I think in this example, it was made minus C1, just to stay with these early. It went minus C0, I'm sorry. I'm sorry. It went from C0, C1, C0. The reflection coefficient became negative of what it was here. So, for a problem like this, the linear term is going to look like this. Alpha 1 of z is going to be 4R1 h of z minus a from the first primary, and from this primary, it's going to be 4R2 prime h of z minus b prime. In other words, it's going to take the amplitude of this event, which is this reflection coefficient times transmission, yes? R2 prime is R2 sandwiched with T01, T10. In other words, the data here is R1 delta T minus T1 plus R2 prime delta T minus T2. T1, T2, R1, R2 prime, because the amplitude of this primary cares about the transmission here, yes? That's why there's a prime. Clear? You take this data and put it in the formula for alpha 1, which says integrate the data. You get heavisides, two heavisides. One at the correct location, A, and one at an incorrect location, B prime. Of course, you gave it C0, so it puts it where time and C0, where T2 and C0 would place it. If C0 is smaller than C1, B prime will be too shallow. B will be here, yes? So what happens is when you put this alpha 1 now for the 2 primary case in that second formula, in this formula for the quadratic term, suddenly this gets it alive. This one, for one reflector, only this lives. For 2 reflector, both turn on. In other words, it's interesting. In other words, for one reflector, it says there's no imaging issue. Yes?
As long as your reference velocity is the same as the velocity down to that reflector.
To the first reflector.
If you gave it an incorrect reference.
If you gave it an incorrect reference velocity, it would already say this is an imaging issue. Yes. In other words, if this is C0 and I gave it C1 prime, the second term would light up. Okay. So what I'm saying is the math arrives, yes? We interpret what it's doing by taking a case where we say you don't have an imaging issue. So can we tell which term shut down? Yes? Okay, so you shut down when there's not an imaging issue. And then now we put in 2, where the second on purpose, this will have an imaging issue if I use C0. Suddenly both terms light up. Let's see what that looks like in this slide. So what you're going to see in the next slide is the toughest part of these talks is finding that pointer. Did I put it in there? All right. You see that? Don't tell us we can't solve practical problems. Okay. So this is just saying what I just said, R2, and now this is saying this is what the data looks like, that line 10, data for 2 reflections, and then alpha 1 is a well-located at A with an approximate amplitude at A, and this is a further erroneous, it's more than just a linear because it has transmission, okay, issues in there. And this is mislocated at B prime, too shallow, okay, if C0 is smaller than C1. When you put that alpha 1 in this alpha 2 equation, you get the following. You get this. This is what alpha 2 becomes. So you get one guy, minus 8 R1 squared, trying to fix up that first amplitude. You get, this is trying to fix up the amplitude at B prime. It's trying to take the amplitude at R1 and help bring it in there. In other words, this guy thinks it should be treated just like the first, minus 8 R2 prime squared, right? This guy's saying, you know, you got a transmission issue, you know? So it's bringing R1, which cares about T01, into the game. You follow? To get rid of that transmission, it has to bring R1 in. So the amplitude issue here is more complicated than here, okay? This would be what it would be if if there was no transmission. This is the new story. This term here, this comes from that integral. That integral produced this term. This Dirac delta, it says there's an issue at B prime. There's an issue. When we first did this at ARCO a long time ago, Corrigan, Mattson, Doug Forster, Simon Shaw, we derived this formula, and there was a bad moment. They said, Weglein, you promised that you're going to correct the depth, right? The ISS is going to be a depth corrector. Look what you did. You located the, thank you for nothing. You told us that there's a problem at B prime. I had to figure out what in the world this was doing. You know, what is that delta? So it tells you have a problem there. It turns out that that's the beginning of a mover. So let me explain how that is, yes? This is the beginning of a mover. What is this thing? B prime minus A is something very close to the difference in time, right? B prime is the depth with C0. A is the depth with C0 with this time, right? B prime minus A is C0 T2 minus T1, yes? B prime is using C0 with T2. So this is, what this is doing is it's getting a sense of the duration of the problem it's facing. The duration. In other words, the fix cares about how mislocated, yes, meaning how wrong is your velocity and what is the duration of it, yes? This is telling it you got a problem at this point and this is the duration of the problem, yes? So both of those come into the fix, yes? So to understand what that delta is, I came up with this. Imagine what an inverse series would be trying to do. And in part, this was useful, and in part, this took us off track. Imagine that C0 is this, and what the inverse is trying to do, it has to build a box like that, a box to make it into C0, C1, C0. So the terms, the linear, the quadratic, and so on, have to end up with a box that I add to C0 to make this, yes? So right now, that box is mislocated and it's got the wrong amplitude. In other words, it's got a linear approximation to this thing, yes? And it's too shallow, that first, yes? You get it? The box is, it's at B prime, not at B. So I imagined that somehow the inverse scattering series, if I was just interested in not fixing that amplitude, but just if I was interested in locating this B, that I'm interested in a location-only subseries, that location-only subseries I would want it to keep the amplitude of this linear thing, but just fill in that box, yes? Move it from the wrong to the right. Make a box, yes? So make a box, that's what a make a box is. In other words, h of z minus b minus h of z minus b prime would be the box between b and b prime, yes? So if you imagine, which I did, imagine hoping that's what the series is interested in doing, to make this box to get this move from the wrong depth to the right depth. Imagine that it's a Taylor series. In other words, this thing looks like a Taylor series about z minus b prime, you could say. It's like f of x minus f of a. See, I rearranged it so it looks like f of x minus f of a. And then this is the a. So it becomes this, the function this is the function at A, and then we need the derivative of the function, the derivative of this at this value, yes, times the difference between z or x and a, which is this. You understand? A Taylor series in the difference between mislocated and actual depth. So this thing looks like what you had that alpha 2 produced. This looks like you see, that looks like, that's what I said, that must be trying to make a box. This is the width of that box. This R1 is some kind of giving me help for the size of the issue. In other words, the mislocation, you're not allowed to find C1. The whole promise is you're going to do all this stuff without knowing the medium, yes? So you're not allowed to look for C1. A normal person would say, you got R1, try to invert and get C1 out of it, yes? The whole idea is the inverse scattering series says in terms of data, without interrogating the data for what caused that data, go and achieve processing. So let's go back to that series. So we imagine that the series is trying to make an expansion in terms of the difference between mis and actual location, mislocation, actual, higher terms, derivative of this, and so on. And but this is not what we have. How are you going to make a series in terms of b prime minus b? You don't know b, yes? You have to make a series in terms of your data, yes? It's an invert, yes. So what you do is you take this b prime minus b, which is what you wish you had, yes? And you expand it in terms of things you have. In other words, you can re-express b prime minus b in this form, b prime minus a, with this factor. Just trust that that algebra is true. In other words, this R1 cares about C0 and C1. You understand? This is just an algebra thing. B prime minus a we have. B prime cares about C0. A we have. So we have this, yes? We also have R1. Why? Because we have the data. We have the reflection from each reflector, yes? So this is a series. This quantity here is the thing we're after is now being written in terms of things we have. This is a series in terms of your data. Linear, quadratic. This is just the data from the first reflector. Why should that come in? Because it's information about this reflection coefficient that's going to fix that depth. Yes? You understand? This reflection coefficient is not going to fix its own depth. That reflection coefficient carries information about C0, C1, yes? Without finding C1 is the point, yes? Directly in terms of R1. So what you see here is that the imaging series is cascaded. What does that mean? You got a b prime minus b, b prime minus b squared, and so on. Do we see that? Yes? A shift between a series, yes? And then each b prime minus b is a series. So it's a series within a series, yes? You follow? Each b prime minus b is in turn a series in the data. So it's cascaded. So when you see Simon Shaw, LOIS, right? Leading order imaging series. What he did is he took within each of these a first order in R1. Yes? When you have Professor Feng Lu doing higher order, he's taking within each of these b prime minus b a higher term. Yes? You understand? How many terms do you need? You need enough terms to deal with the duration and the contrast, okay? How do you know enough? That's what we'll see. In other words, how do you know how many terms? So let's now look at some examples, yes? I'm giving you some sense of how the machine works. It does this. B prime minus B, you don't know B. That's what you want. This is a shift between the wrong location and the right. Make that box move, yes? A difference of heavisides. That is if you like, a power series in B prime minus B. You can't supply B prime minus B because you don't know B. If you knew B, you wouldn't have a problem at depth. But what you do know is B prime minus B can be written in terms of B prime minus A, which you do know, and this. And then this guy is a series. R1 is data. B prime minus A is just T2 minus T1, essentially, times C0. So you recast it in terms of information you have, yes? That's what ISS depth imaging is doing, yes? In a nutshell. Let me show you some examples. This is the famous Simon Shaw movie. This is, we're going to tell you, oh, there goes the movie. It went by itself. That's amazing. It knew I wanted it. We're very close, this algorithm and I. Okay. This is a model where it starts with water, gets faster, faster, slower than water speed, and then back. So this reflector is less mislocated with water speed than this, because this going this way, the overall average error to this is less than it is to this, because greater, and suddenly less. So the average velocity, if you like, to this is less. So what you see in the middle panel is a water speed image. Water speed image from the primaries of this model. So this one is well located because it's water bottom, mislocated, further mislocated, less mislocated. Yes? For the reason I mentioned. Then you start putting in terms like that delta, z, you understand? Terms that deal with imaging. And the movie represents sums of terms, yes? The quadratic plus the cubic, yes? And what happens? This image multiplies itself. In other words, it's alpha 1 times alpha 1, yes? There's an alpha 1 derivative, integral alpha 1. It's always images communicating, yes? In a certain prescribed way to deal with imaging. So the movie, what's going to happen here is this one will stop asking for terms before this on its own. In other words, it looks noisy because of all that delta stuff, okay? It's band limited singular, yes? Things going on. I don't know how we got this to go. It went by itself. Oh, there you go. So you see, this guy is happy. So this is like a group therapy session with this talking to itself. Each of these is talking to shallower. In other words, it's talking to the corresponding, like R1. There's R1, R1 squared, trying to fix that depth. Yes, powers of R1, yes, in those B prime minus B terms, yes? So what happened is, this one decided that it was at the right depth, while this still needed more terms, yes? And this, let's show you the pre-stack. That'll give you a hint. The pre-stack of this, these are the terms adding. Again, you see, what happens is, this has a move out when it's not happy. For this direct inversion, when it is happy, when it is giving you the right depth, the common image gather is flat. The common image gather being flat is a necessary and sufficient condition that a direct inverse method has achieved its goal. So this one gets flat, And this one still has a move out, more terms. As soon as this is flat, it will take no more terms in. In other words, it stops further terms from entering. You know, it's amazing, yes? In other words, after it was doing it, we looked in and said, well, how did that happen? You understand? We didn't stop it. It stopped when it was flat. So, this model, this degree of capture is called LOIS, for leading order imaging series, yes? It works for relatively small differences between C0 and the velocity, yes? And small durations. Two things happen when you have bigger duration or bigger contrast. First, LOIS will never flatten. You understand? You can give it many terms, yes? And it's always giving you a move out, yes? You understand? It's just needing higher terms of R1 squared, R1 cubed, yes? So you know that because it doesn't flatten, yes? So then along comes Professor Fang Lu and captures higher order terms, yes? And is able to deal with big contrast and bigger duration. There's another issue, though, that we haven't talked about in the past, but it's relevant for today's discussion. Something in addition to not being flat happens, yes, when you don't give it enough help. In other words, the leading order imaging series is able to correctly produce depth for just a certain range of difference and duration, yes, a certain range. If you give it a bigger duration or bigger, it's beyond its ability, yes? You need a different collection of terms, yes? Higher order terms. But something happens besides it not giving you the right depth, keeping move out, you understand? If we made that bigger, these things won't get flat. Not with Simon's code, yes? Just won't. It takes higher order. But in addition, something strange happens. This guy starts to ask this individual for help. It starts to ask deeper things for help. That makes no sense. That's a breakdown. Okay? The thinking is all the assistance that it needs to come shallower. Yes? When you do the higher order terms, that request from deeper stops. In other words, when you put higher order terms, two things happen. You can deal with bigger difference between actual and reference, bigger duration, and no more talking with deeper to help shallower. Yes? This kind of issue is always there in ISS. I'll give you a for instance. If you look at the internal multiple algorithm, yes? The internal multiple algorithm. And this is something Yi Lo from Saudi Aramco was furious with us about, because he was a big advocate. He and Chung Fu, they published the first land data, yes? Then they ran some tests, very complicated tests with that B3, and they got very strange results. What happened is, if you have B1, B1, B1 in that B3 formula, yes? That thing is working on primaries, yes? This primary plus this primary minus that primary. Well, what if you have an internal multiple that goes in there? Your data is not primaries. If you could put primaries in, we wouldn't need to get the multiples out. All the data goes in that algorithm. When you have internal multiples as sub-events, that B3 can cause mischief. It can predict events that are false. It's just beyond itself to deal with. It can deal with primaries in it, yes? Hung Liang here, and Dr. Hung Liang and Dr. Chow Ma located higher order terms in the series that anticipate that problem and remove it, yes? They're actually there to deal with the issues that internal multiples being treated as sub-events can cause in that one term. In other words, there are issues that are beyond its ability, yes? Other terms of higher order, yes, are designed. They looked for the negative of that issue in the series, you understand? But and they have an algorithm which they call comprehensive internal multiple elimination. You said the word comprehensive because it's dealing with internal multiples being treated as sub-events, which can cause an issue, yes? And they include higher order terms that deal with it, yes? So I'm saying every time we have a term in the inverse scattering series, it has an ability, but it also has things that are beyond its order. Beyond that number of datas times data can do certain things with 3 orders and certain things it can't, yes? It needs higher order to deal with the issues that are beyond itself, yes? So that talking to deeper, yes, is a problem, like producing false events in B3, yes? That Yilo is very upset about. And so when you take higher order, it does both bigger contrast, bigger duration, and stops the talking, yes? It doesn't allow the talking for deeper to fix shallower. You understand? Shallower have information that this needs in terms of reflection coefficient to fix that depth. Deeper it's got more problems than, it's got its own problems, yes? You understand? You follow? So that's going to turn, I'm making a belaboring that issue of talking about deeper because it's going to come out to be what we need to address in a multi. So let me race on. Here you have Professor Fang Lu's salt model, big contrast, yes, compared to Simon, because these have higher order terms. Here you have a water speed migration, top salt mislocated. Here you have all this, the fractions heading off here, yes? Yeah, mislocated. This guy here is up here. This guy. And this is Professor Fang Lu's higher order. Higher order doesn't mean all order. It's higher order. There are laterally, there are terms for lateral that are not in. This is mainly for correcting depth, not lateral issues. There are terms like partial respect to x, partial respect to y, terms in the inverse series, directly looking for issues of lateral mislocation, yes? So, but this is certainly an improvement. You can see this is where, yes, has happened. There's still issues here. Zicheng Wang, who's a PGS, plus lateral exclusive terms. Not all, but there's an improvement, yes? So as more terms are added, you get the ability to accommodate more issues, yes? All of this is assuming only velocity varies, okay? That the only unknown is velocity. And so we'll just race through. This is a false shadow. This is water speed. This is Fang. This is Yicheng. Okay, then there's Mamusi. Let me get to very encouraging here results. This is the water speed, and this is the HOIS. For away from here, you're getting very encouraging results. There's a lot of rapid lateral here, yes? How do you know what's working and isn't? Take a section and look at a common image gather. Look at 3 here, here, and here, yes? Look at different subsets of the data, the image. Where it's flat, it's right, and where it's not flat, you have issues, yes? It doesn't have enough terms, yes? So, this is multi-parameter. Haiyan Zhang, Shu Li, Hong Liang, who's here. Why do we need this? Before the lunch, I mentioned this thing is talking to reflections above it, yes? If you're interested in the location, there should be certain reflections that are not in that conversation. Yes? If it's density only, you don't have an imaging issue. C0, C0, C0 will get everything right, yes? So if you have an inverse machine, which is only velocity, it thinks that every reflection is due to a velocity change, because you told it the only parameter is alpha, yes? So it doesn't have a way of excluding. As soon as you allow here velocity and density to both change, here's relative change in bulk modulus and density linear, yes? This is quadratic. Look at this. Look, please look at this and this. This is G0, V1, G0. This is G0, V2, G0. If you can solve for alpha 1 and beta 1, you have the same exact machine to solve for alpha 2, beta 2. It's the same sandwich, yes? Remember that? G0, V1, G0, G0, V2, G0, yes? It's the right, but here's the key. Once you allow in your inverse machine that velocity and density are both variables, yes, and unknown, then it will eject any reflector that's only density. Watch. Once you say velocity and density can both, this is some smart machine. You understand? I guarantee you we couldn't cook this up. We just derive it, yes? And then we say, so watch how it does that. First of all, these integrals represent moving terms, just like that first thing. Alpha 1 squared was an amplitude. Why is an integral moving? Because mislocation cares about duration. It's an integral over things. Alpha 1 squared is like an amplitude. Just fix the amplitude at A. Yes? You understand? A duration, in other words, to fix a mislocation, it has to integrate over the issue. You know? There's a duration to the problem. There has to be a duration to the fix. Yes? Integrals represent duration, integrating over issues. It's not a local thing. It's how long has this issue been going on, yes, in the layer. So here are two integrals. And these integrals, in fact, can combine. I don't know if they combine like this. What this is a reflection coefficient. This is basically the data, differentiated. If you go back to that thing on top. There's a thing outside, it's like a reflection coefficient. It wants to know if it has been mislocated, like before it was alpha 1 derivative. Now it's generalized to this. But this is the key. Please look at alpha 1 minus beta 1, the integrand. Let's take a look at for alpha 1 minus beta 1, the linear approximate to the change of bulk modulus, minus the relative change, the linear approximation to the relative change in density, is the linear approximation to the change in velocity. But that's irrelevant. In other words, we can show you that. Just look at what velocity looks like, the square root of bulk modulus over density, and blah, 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 yes? But the important point is that quantity, alpha 1 minus beta 1, occurs in this integral, yes? In this moving term. So watch what happens to that term. You have a data. What happens here is that first term, you have to solve for alpha 1 and beta 1, yes? To put in here alpha 1 minus beta 1, yes? I have to solve that equation that data is linear, has a combination of alpha 1 and beta 1. You give me data at one angle, give me data at another angle. I have two datas, yes? Alpha 1 and beta 1 are not functions of angle, just functions of depth here, yes? So I have two equations and two unknowns, and I solve for alpha 1 and beta 1. The data here is going to be essentially very close to a reflection coefficient for one interface, the first interface. In other words, there's if you look, the data for the first interface is going to be r of theta, h of z minus a, the shallower one, yes? This is just like r before h of, the data here is going like alpha 1, yes? Data, alpha 1, yes? Alpha 1 steps, yes? Boxes. But here's the point. Here's an acoustic reflection coefficient, a perfect formula, yes? This is like Zobrist for acoustic. This says the reflection coefficient, perfect reflection coefficient across a boundary, cares about C0, C1, rho 0, and rho 1, and angle. This is the formula, okay? That's not an approximation. If the velocity doesn't change across the boundary, yes? If C0 is C1, meaning density changed, but not velocity, yes? A density only change. Do you understand what I'm saying? Let's say density changed across this reflector, but not velocity. If the velocity didn't change, this is 1. Yes? If the velocity didn't change, this is 1. And then you have a factor 1 minus sine squared that factors out from numerator and denominator. Yes? If C0 is C1, the point is the reflection coefficient is independent of angle. Yes? You follow? What is alpha 1 minus beta 1? If you go back and solve that equation on there for alpha 1 and beta 1, you get a formula that says alpha 1 minus beta 1 is r of theta 1 minus r of theta 2 divided by sine squared theta 1 minus sine squared theta 2. Just do the algebra. R of theta 1, r of theta 2, two equations, two unknowns, solve for alpha 1 and beta 1, and then subtract them. You'll get this formula. So what does it say? If you have a density change, but not velocity, if you don't have a velocity change, but you have a density change, you're going to get a reflection coefficient. But you're going to get a reflection, but it will not be a function of angle. Yes? If it's not a function of angle, r of theta 1 is r of theta 2, and the numerator is 0. If the numerator is 0, alpha 1 minus beta 1 is 0. And this says that reflection doesn't contribute. You see? Once you set up to give it the potential to have velocity and density, and you ask it to do imaging, it will automatically exclude a density-only change. That's pretty cool, yes? The same thing happens in the elastic case. This is elastic, okay? Where these changes here look for velocity change. Only velocity change, whether it's VP or VS, you understand, will allow a reflection to be in the conversation. If it's a density only, it's out, okay? So that's interesting. And there's examples by all the people who are on this slide: Haiyan, Xu Li, Hong Liang, yes, Shanzong Liang, people who went and looked at that in detail, the imaging. So here you see examples where you have a constant velocity, and the water speed image is the image. HOIS just says you got the right answer to begin with, okay? Doesn't move anything. Constant density, but variable velocity, it fixes. This is velocity and density both varying, and it fixes, yes? It produces the right depth, and so on. This was, Doug had asked, stop worrying about AVO. There are issues less challenging than AVO that are causing us issues. We can't tell type 1, type 2 AVO. We just can't see it. A type 1, type 2, if I remember, have zero crossing, a polarity change. What happens is, in the migration, there's when they try to flatten it, they get these bumps because of the velocity wrong, yes? And eventually they just iron it. Iron it. Like your pants, they just iron it, okay? And that zero crossing can disappear in that smoothing process, yes? So what this showed is this on purpose had a zero crossing, yes, at the wrong depth, and the ISS produced it at the right depth and kept the polarity reversal, yes? It wasn't ironing or finding a velocity. Anyway, Kristen, let me just say, there's a paper, you have a copy, which argues in detail why that shallow water North Sea was working, okay? It was working, it gave you the right depth. It gave the right depth if we assume the first mislocated reflector is due to a velocity change. Okay? You say, well, why did you have to worry about that? I thought you had all this multi-parameter. Let me tell you why, okay? We had to worry about it because the first term in finding that alpha 1, beta 1 needs angles, yes? One angle, another angle, right? Two angles. On synthetic data, you can pick angles very close, yes? What can happen in multi-parameter, right at the linear step, is in field data, you can't make them too close. If you make them too close, you're not going to get difference in data. The noise, you have to have a difference in angles sufficient that you have different numbers, yes? Synthetic doesn't have that issue. So, but once you make the angles big enough, it turns out that this talking to deeper can come in. Okay? Talking to deeper comes in at the linear step. Okay? At the linear. That issue is due to the fact that what we're looking for are boxes. It turns out. Okay? This box business. We're saying make a box and then look at the location, the ends, okay? That is a space filling function. In other words, the thing we're looking at fills space, you understand? And that causes issues. If we input, as you'll see in a minute, Dr. Chalmers showing, reformulate it instead of this alpha business, alpha 1, input it as a water speed migration, and then ask it to do inverse on it. Make it well located at depth, and it's going to be fascinating to see what Dr. Chalmers shows you it does for the amplitude. In other words, treat the input as a water speed migration, you're going to avoid the issue of talking to deeper, yes, which was the impediment before. Then we're going to run through all this LOIS, HOIS experience, yes, with that multi-parameter that doesn't have a talking issue with deeper. So you say, well, didn't you have a talking issue with deeper before? Yes, we did. Simon Shaw had a talking issue with deeper, but it already had some region of working, and we knew more terms could fix it, and did. Here, the linear term has that issue. You understand? That tells me you got to start in a new spot, yes? If the linear term has an issue, you understand? That's more serious than when some gathering of terms has an issue, and then more gathering can remove it, if you get my drift, yes? So this is an introduction to Dr. Chalmers, who's going to tell you what happens when we reformulate, just the beginning. Just start from the beginning, no more alpha 1, alpha 2. Look at migration as the input. Now, alpha 1 is a box, you know? That's the issue. It's space filling. And that space filling is why a deeper thing came in, yes? It was, you'll see a picture. Okay, so this is a complicated subject. I gave out a copy, a reprint of that paper which delineates why there was a viability test. What do you mean viability? It dealt with bandwidth. It had a common image gather flat where it wasn't with water speed, and then flattened. So common image gather flat will indicate that you have the right depth under certain conditions. Condition 1, you have to have the right Earth model type. If you assume only velocity, and it's velocity and density, you'll get common image gather flat and it won't be the right depth. You got to have a match between Earth model type. So, and it has to deal with low frequency because of this box business. The migration input is not going to have that issue. In Let me just explain. The first step here is alpha 1. Alpha 1 wants low frequency. You understand? Wants a jump. If you don't give me a jump, those integrals don't know what to do with themselves, you know? So to build a box from the wrong to the right depth is a story that starts with a linear estimate of a box. Yes? If I have missing low frequency, you don't have alpha 1. You understand? So Professor Fang Lu found a way to regularize for that issue. But that issue is avoidable. So let me explain. We'll look at the same problem now, but instead of these boxes, look at it in terms of migration. This will take 1 second, and then Dr. Chow Ma will speak. Let's say you have a migration to the water bottom, the A thing. This is some migrated result, 1D normal instance. And then you have this mislocated, this is at A, and this is B prime. This is a mislocated spike. No boxes anymore. You understand? That box business, and we had to make it from the wrong box to the right box, yes? You're right into the build boxes story. You understand? What we want is, don't mess with this guy's amplitude. We're only interested in locating it. Put it where it belongs. With this amplitude that we know has transmission and everything on it, don't worry about that. Just try to find structure, yes? So we want this to be at B, yes? So the process that has, if this is the first term, the process we want has to remove this and make this. Remove this. So the process has to do this and this. These are equal amplitude. The zero frequency of that is 0. It has no zero frequency interest. Contrast that with B prime B. Make that the first estimate. Where's the low frequency? Yes, the alpha 1 needs a jump. Okay? So in addition to not speaking to deeper, this spike reformulation is going to avoid low frequency sensitivity. Okay? Okay, so with that, I'll introducing Dr. Chow Ma to show you a very interesting result. In other words, you reformulate in terms of migration, you ask, what is it going to think to do with amplitude? Yes? What does it think it needs to do to a migration? Yes? Watch what the inverse series does. This is totally what the inverse series decided it wants to do for a migration input. Fascinating. It's got its own brain. I didn't know whether it was going to try to invert, find alpha or something. Watch what it does. Dr. Chow Ma, yes.